Stuff like that throws me. I have like an order. Okay, so two more lectures. So this lecture we're going to be talking a little bit more about alternating series. And in particular, I'm going to give you the alternating series test. So what did we learn anyway? What did we learn yesterday about alternating series? Can anyone recap us?
Absolute value A and B. And then A and B without the absolute value, and if it's multiplied by a negative, it's definitely convergent because it's going to be smaller.
Okay, something like that. So we learned yesterday that if you have a series and some of the terms in those series are negative, you can just assume they're all positive. And if that series converges, then the original series converges, right? So given a series with negatives in the terms, you can use all of your old tools, which are tools that only work on series with all positive sums. And then I gave you two tools, I think it was the ratio test and the root test, for determining if something converges or diverges. But you can still use your comparison test, and I don't know if the first one has a name, but where you check that the limit is going to 0. So today we're going to talk more about what to do in cases where, so we talked about this one, this sum. Let's start at 1. Yeah, 1 minus a half plus a third minus a quarter plus a fifth minus a sixth, and so on. We talked about this yesterday, yeah? It's an alternating series. Is it a convergent alternating series? Well, what is, so if this is the, I guess this is sum, this is the sum of k equals 1 to infinity of 1 over k times minus 1 to the k plus 1. And it's the alternating harmonic series. So what did our absolute convergence test say? It says, well, if it's the case that the absolute value of this, which ends up being 1 over k, if this is divergent, if this is convergent, then this is convergent. That's what the absolute convergence test tells us. But what is this? It's the harmonic series. And what do we know about the harmonic series? It's divergent. So if this is S, then the absolute value of S is equal to this, which is divergent. Okay, so we can't now conclude that this is divergent, right? Because this is bigger than this, right? We could have got lucky. We could have got lucky and found that the bigger sum was convergent and have concluded that this was convergent, but that's not the case. So I have to give you an extra tool called the alternating series test, which you use when all other tests fail, essentially. Right, this is the last resort. So I'm going to tell you that this, which is called the alternating harmonic series, this is convergent, and I'll show you why. But so yesterday I asked you a question. Can you give me an example of a series that's not absolutely convergent, but is what we're going to define today to be called conditionally convergent? It's this. That was the answer to that question. So it was actually motivating today. Any ideas how we could show that this is convergent? It's cute.
The negative sum is always bigger than the positive one, except for the one that we start with.
The negative sum is always bigger than the positive one. Well, how would that help?
Well, that means that it's going to cancel out, and then we're going to be left with.
Yeah, that's what we have to sort of look at. We have to see what's the difference between the positive sums and the negative sums, and hope that the difference of those two things sort of disappear. Yeah. Okay, so I'm going to show you that this sum and I use different index variables just to get you used to the fact that we can be using index variables, so you don't get freaked out if you see a k or an I or an n on your exam. So we're going to prove that this is convergent. And I'm going to do it. It's kind of fun. Okay, so that's sum. Let's call this S. I'm just going to rewrite it. This is 1 minus a half plus a third minus a quarter plus a fifth minus a sixth and so on. And what I'm going to do is I'm going to group these terms. So I'm going to say this is minus a half minus a third. Can everyone see how that has happened? Right, because I just sort of, that minus will distribute to that half, and this minus will become a plus. I'm going to subtract this quarter minus this fifth. And I'm going to subtract a sixth minus a seventh, and subtract, what's the pattern here? Anyone can see a pattern? Can anyone count through the denominator for me? 2, 3, 4, 5, 6, 7. Can anyone deduce the pattern? What should this term be? All right, I'll tell you, but I don't believe that you don't know. Maybe you're just tired. It's an even number followed by the next number. Right? So the thing that we have to be careful about is it is like k and k plus 1, but we have to make sure that this guy is even and the next thing is odd. So we have a standard way of writing this. So it's minus 1 over 2k, that's even, minus 1 over 2k plus 1, that's odd. Right? Just so we have the signs correct. And then we can continue subtracting. Okay, but we can do a little simplification here. What happens if I combine this fraction? What is 1 plus 1? Okay, what is 1/2 minus 1/3? Okay, answer me this question, and then I will stop asking you questions. Just need to know that someone has a pulse. What is 1/2 minus 1/3? Thank you. So I guess these guys are zombies, and these are zombies who know math. All right. This is a sixth. Well, 1 over 2 times 3. This is actually, so the 5 will go here, the 4 will go here. So we're going to get 1 over 4 times 5. Here you're going to get 1 over 6 times 7. And then eventually you're going to have 1 over 2k times 2k plus 1. Everyone see the pattern? No disagreements? Okay, so what I can actually write this sum as now then is this. This is actually equal to the sum, this is actually equal to the sum of 1 minus the sum, k goes from 1 to infinity of just that, 1 over 2k plus 1. Everyone agree? Yes. All right, that's just the pattern. Can anyone tell me about the convergence or divergence of this guy? Okay, I'll expand it a bit. So this is going to be 1 minus sum 1 over 4k squared plus 2k. How would you attack this one? All right, well, I'm going to do a little lemma. A lemma is just like a little sub-result that we need to prove this. And I'm just going to prove, since we feel a little bit uncomfortable about this, I'm going to prove that this converges. Pardon me? Oh, 2k. What's the limit comparison test? Anyone remember?
Oh, the limit of the sum is the same as the limit of the...
Yeah, more or less. So if I have two sums, right? Two series, and I take the limit of their, the ratio of their terms, and that limit is finite, then those two series diverge or converge together. Does that ring a bell somehow? Okay, so I want to say something like this sum converges with comparison to the harmonic series. With comparison to a p-series. Right? Because notice, if I have, okay, so notice what's true about this sum. Why? Yes, this is a convergent p-series. How can I then use the fact that this is a convergent p-series to demonstrate that this converges?
Because the one above only adds to it. Adds to the denominator, and that makes the value smaller.
No, don't argue, right? Just tell me what test. I've given you like 5 or 6 tools. When you're given questions like this and I say like demonstrate convergence or divergence, don't start arguing. You have like 5 or 6 tools. Use one of them. We'll usually tell you. Yeah, it's the limit comparison test. That's what I prompted this, right? So we then look at the limit of k goes to infinity of this divided by this, right? So it's going to be k squared divided by 4k squared plus 2k. It's technically the absolute value of this, but it's all positive. What's the limit of this? A quarter. Which means by the limit comparison test, this sum and this sum, right? So this implies by the limit comparison test that this and this converge or diverge together. And since they converge or diverge together, and this is convergent, then this is convergent. So we have that 2 is convergent. Okay, so I've proven my lemma that this is convergent. But what does that mean about this?
That's convergent.
Well, this is convergent. That means it's finite. I'm removing it from 1, which is still finite. So this is equal to this, which, by the lemma, is convergent. So what have we proved?
The alternating harmonic series is convergent.
The alternating harmonic series is convergent. It's not, however, absolutely convergent. Okay? Did everyone see that? So this is we have a bunch of standard examples. So the harmonic series is a standard example of a divergent series. The alternating harmonic series is an example of a series that converges, but does not absolutely converge. Okay? So we have a name for this. I haven't even looked at my notes yet. All right. Jumping a little bit ahead. So this is called conditional convergence. A series, sum an, is conditionally convergent when sum a of n converges and sum an diverges. So that is to say something is conditionally convergent when it is convergent but not absolutely convergent. Right, so now when I give you a question, yes sir?
By absolutely convergent, do you mean we just look at the original series?
No, I mean we look at the absolute value of the series. Absolute convergence.
Okay. Oh, I see, because then the negative one would end up being
Yeah, so the absolute version of the alternating harmonic series is just the harmonic series. You just assume all the negatives are positive, so it makes the sum a little bit more easy to handle. But it could be the case, I just showed you a case where the absolute convergence test fails, or like the absolute version of our sum is divergent, but the alternating version is convergent. Okay, so what do we do then in situations like this, where the absolute convergence test fails, but we still don't have enough information to conclude if our alternating series is convergent or divergent? You basically want to do this, but you don't want to try to figure this out every time. So this basically is the proof of the alternating series test. The alternating series test is basically the generalization of this idea, that if you have an alternating series, you need to look at the space in between consecutive positive and negative terms and hope that the difference is shrinking somehow. Right, so the theorem, which we call, what was it, alternating series test. And they'll always have three conditions. Alternating series test, which I'm just going to write as AST. Okay? So there's a little bit of a new notation. So we're going to write an alternating series like this. So we're going to go from k equals 1 to infinity, minus 1 to the k plus 1. And then instead of writing an a in here, I'm going to write a uk. Why am I writing a u? Well, I want to emphasize that these summons, or like these terms, are positive. They have to be positive. All right, so this is going to be something like u1 minus u2 plus u3, and so on. So importantly, this uk here is positive. So this will conditionally converge. Actually, it's not. I guess it's just telling you if it's convergent. You still have to do a test. Will converge when, I guess I could say it at least conditionally converges. When, now, three things have to be satisfied. And when we go through examples like this, we're going to really be careful to go 1, 2, 3. So the first thing that we have to check is that the UKs are indeed all positive. That's the first thing we have to check. The second thing we have to check is that the U's are decreasing. So I need to check that UK plus 1 is less than or equal to UK. So i.e. UK is decreasing. Eventually. Does everyone remember what this means? You can have a finite number of exceptions. Like you can start this at 60 if you want. Right, so we've used this term a bunch. And the last thing we have to check is that the limit of k goes to 0 of UK is 0. But you should check this every time anyways. Right, the first thing that you should always do when you're given a new series is try and determine if their terms are converging to 0. Okay, so I'm going to erase the boards. I'm going to leave this here. Try applying this to the alternating series and see what you get. Right, the alternating series is that one. Right, so just make sure that, let's confirm that the alternating series have these three properties. It should be very easy. Go. Okay, so let's apply the alternating series test to the alternating harmonic series. So we have the sum of k goes from 1 to infinity of minus 1 to the k plus 1 over k. So the first thing that we have to do is determine what the UK is. So what is UK? It's the terms, but only the positive versions of them. We're just going to ignore the fact that there's an alternating sign. It's easy to extract it, right? Like, if you're given a sum like this this means that un is just going to be the absolute version of an, right? Just drop the positives. So, exactly. Okay, so we have un here is 1 over, I guess it'd be uk, is 1 over k. So, can we demonstrate, how do you demonstrate 1? Well, I have to show that this is greater than 0, right? Okay, so the assumption is that k is going to be greater than or equal to 1. That's our counting variable. Right, so if k is greater than or equal to 1, this means that 1 over k is greater than or equal to 1. I just divided both sides by k squared, which is positive. Right, so you're allowed to do that. Everyone see my argument? I see you squint. Look at this. Divide, and when I'm allowed to multiply or divide by things that are positive without switching the equality, yeah? So what happens if I divide both sides by k squared? Oh, that's totally wrong. Yeah, no wonder you're confused. Well, if k is bigger than 1, then certainly the fraction is bigger than 1. Yeah. So I'll just leave it at that, which means that uk is greater than or equal to 1. Right, so this means we have 1. Okay, what's the second thing that we have to determine? We have to prove that uk plus 1 is less than or equal to uk. So this is going to seem like magic, but essentially what you got to do here is like work things out backwards and then write it forwards. But okay, never mind. I'm going to show you a way to do this, which will usually work. So you want to show that uk plus 1 is less than or equal to uk. Now you noticed I've always normally drawn arrows in a forward direction, meaning that if this is the case, then this is the case. There's a stronger version of this where the arrows go in both directions. Right? Like, so this will be true only when this is true. Like I'm basically saying these are going to be equivalent statements. So uk plus 1 is less than uk only when 1 over k plus 1 is less than or equal to 1 over k, which is only true when k is less than k plus 1. And is that true, the last thing? Okay, I can go one more. Let's go one more. This is only true when 0 is less than or equal to 1. Is that true? Okay, so at the end of this chain, I'll just say that this is true. Right? So what we have proven is, given it's true that uk plus 1 is less than or equal to uk. Right? That's how you produce that argument. You don't really have to give an argument this nice, but you definitely have to at least state that that is correct and argue if it's non-obvious, right? Because here, I would, like, if you just went UK is positive, that's fine. It's very clear. Okay, so what do we have here? We have that it's true that 2 is the case. What's the third thing that we have to check? Yeah, we just have to check that the limit of un goes to 0. So is it the case, what is the limit of k goes to infinity of 1 over k? That's 0, which means that we've satisfied 3. So, by the alternating series test, we have that this guy, what? Converges or diverges? Converges.
So this is not as important, but how can 1 be bigger or equal to 0?
It's saying it is true that 1 is bigger than or equal to 0.
And would they equal sign? Would they equal?
Is 1 greater than or equal to 0?
It's bigger than 0?
Yeah.
Greater than 0?
It doesn't seem you know how OR works, right?
Okay. I mean, sure.
Is this a cup of coffee or a microphone?
Yeah, but we know it's not equal to 0, so why would we include that? It's okay, I said it's not important. I was just wondering why it's there.
But it's still true. All I care is that it's true. I need this to be equal in order for here to have equal.
Oh, okay.
Although, like, it's both are true. Like, if I removed all the equals, it still works. But again, right? It is true that this is a coffee cup or a microphone. I know that's kind of weird, but that's how OR works. It is not true that this is a cup of coffee and a microphone. But to be honest, I've never tried drinking my microphone. We can give it a try. Okay, so this converges by the alternating series test, and it was the most trivial example. Let's do a less trivial example. Okay, this one's a little bit more tough because we're going to have to use a lot more of our tools. What about this one? Sum minus 1 to the n over n ln n. And n goes from 2 to infinity. Okay, so let's do this one together. We'll just walk through it. What are the three things that we have to hit? Okay, so the first thing that we should do is actually write down what u is. Right, so in this case, what is u of n? 1 over n ln n. Is this positive for all n? Yeah, maybe we should do a little bit more work here, right? So if I know that if n is positive, if n is greater than 2, this actually implies that ln n is greater than or equal to 0, right? So it's ln is positive after 1. So it's definitely positive after 2. And this means that n log n is greater than 0, right? Because n is positive as well, which means that 1 over n log n is greater than or equal to 0. Again, your arguments don't have to be as robust as this, but you definitely at least have to say that it's positive. I'm just trying to make sure I'm showing you exactly why it's positive. Can you follow this argument? Okay. Okay, so we have that. So this means that un is positive for n greater than or equal to 2, which means that we've satisfied condition 1. Okay, next condition. What do we have to show? Pardon me? Yeah, we have to show that these are decreasing somehow. So can we show that un plus 1 is less than or equal to un? How can we do this?
Well, we use the same argument we used there. We showed that 1 over
Yeah.
n plus 1 ln n plus 1 is smaller than 1 over n.
Okay, so this is true only when it's that this is, oops, I missed some pluses. So if this is true, it will be the case that this is true. Jeez. And plus 1 over n log n. Okay. This is only true when n ln n is equal to n plus 1 ln n plus 1. Now, I think this is obvious enough. Do you? Like, is everyone comfortable on like just seeing this as being a true statement? Right? Like this n is smaller than n plus 1, and this thing is smaller than this. Right? So both of these things are correspondingly smaller than both of those things. So I don't know, I'll put some dots, maybe if you want to put in more details, but eventually this ends up being true. Right? So that means this is true, which means we have 2 is satisfied. What's the last thing that we have to prove? Yeah, the last thing we have to prove is see if this limits to 0. So what is the limit of n goes to infinity of 1 over n ln n? Which is 0. This means we've proven 3, which means by the alternating series test implies that this n equals 2 to infinity of minus 1 over n ln n is what? What have we proven? Yeah, that this is convergent. But now I want to be more specific. What type of convergence do we have here? Do we have conditional convergence? Or do we just have absolute convergence? Absolute convergence being the stronger thing. So how can I conclude here that this is conditionally convergent and not absolutely convergent? Okay, let's start at the beginning. What does it mean to be absolutely convergent? Right. Okay, so this is at least convergent, but now I want to see, like, are we only conditionally convergent, which is a weaker type of convergence. So let's check absolute convergence. We actually should have done this first, because if the series absolutely converges, then it also converges with its alternating terms. Right? So like really we're using these this test as a last resort. Right? Well, we'll do a full example where we'll start from scratch, not knowing what happens, and I'll show you all the tests that we have to go through before we get desperate enough to use this one. Okay, but how do we check for absolute convergence? We have to ask about this sum, 1 over n log n. Does this look familiar to anyone? Well, what about this integral? Oops. This is divergent, this integral. So what can you conclude?
Conditionally convergent. That the whole thing is. Oh, that 1 over n.
If I tell you that this is divergent, what does that tell you about this?
Divergent.
Why? Integral test. Okay? So this is divergent with integral test. Because that integral diverges. Please study this. Right? 8 days. Yeah.
If it fails one of the conditions, does that mean it's automatically convergent? Divergent, or does it mean that we're not sure?
No, notice that I'm not saying that if something fails the alternating series test that you can conclude anything. Right? This is something that says if these conditions are met, then this series is conditionally, at least conditionally convergent. Right? So that's the difference between these type of arrows and these type of arrows.
So what's an example of it not satisfying? Like n plus 1. It's like n plus 1 is not fine.
Okay, so first of all, if your terms aren't descending, period, then we can conclude immediately that the series will diverge.
Yeah, like that's like I can automatically
Yeah.
put that.
Right. So like it's almost, well, which one? This one?
Yeah.
Well, notice that this is talking about, so this is a positive thing. So we're strictly decreasing. If I alternate, we can do this.
Yeah.
Right, so you can have weirder types of limiting behavior. But yeah, the first thing you should always check is that the limit of your summons tend to 0. Because otherwise, there's no chance that the series is going to converge. Right, so we're going to do this in the next example. I didn't want to do everything else because I want to show how to use the alternating series test. For the next example, maybe we'll just start from scratch and do every test. Okay, so this worried me, right, because you need to be comfortable with stuff like this. So remember, if you have a function that goes through each point of this, you can take the integral. Right, now remember that this sum and this integral, well, I guess I should write this, n equal 2 to infinity, these will diverge and converge together. Okay, let's try doing more. Can I write down this board? Because I kind of want to keep the alternating series test up there so I can point at it. Yeah? All right, so digest. Okay, what's our next example? Actually, I'll give you a practice while I wipe down the other board. So give this one a try. And remember, Okay, I'm trying to teach you a lesson here. I've given you a hammer. Everything I give you from this point on is in a nail. Just keep that in mind. Okay? I hope that idiom is universally applicable. I'm sure there are not like hammerless societies. I'll have to look into that. Tell me about this. Is this convergent? Is this divergent? Is this, and if it's convergent, is it absolutely convergent or is it conditionally convergent? Right, so the workflow should always be something like this. Check for divergence trivially, right, by seeing at least that the terms descend to 0. And then when it fails to, if it diverges, then you're done. Right? If it doesn't, if you can't conclude anything, then you have to ask if it converges. And then when you establish if it converges, then you have to ask, does it converge absolutely? Or, which means it converges normally, like this is the better version of convergence, or does it converge conditionally? Right, but these are all stopping points. Right, so if it doesn't converge absolutely, then you should check that it converges conditionally. Right, but each of these are stopping points. Okay, so just keep that in mind. Give that a try. I'm just going to copy these terms over here. You need UK is positive. UK plus 1 is less than or equal to UK eventually. And the limit, k goes to infinity, UK is equal to 0. Don't mean to stress you, but it should be done. That's how easy this one is. No. It's the all positive here for a second. Right. So you can yeah. Just take the the last 2 episodes were terrible. If there's no drama, which is like happy. I see 20 people watching each other. Did I haven't used these? 6 months. All right, so who has an answer for this? Why? Sorry, what kind of convergence? So is it conditionally convergent? No.
Oh, yeah, no.
Conditional convergence means that it converges on the condition that you're not trying to make it absolutely converge. That's the condition. Right? The conditional convergence refers to you need to let the negative terms remain. Under those conditions, the series will converge. Okay, so notice that this guy, the absolute value of S is equal to this. And what is this? Anyone? What's this? Ladies at the back, what's this? Geometric series. Yeah? So what is it equal to? Oh, sure. This is 1 over 1 minus a half, which is 2. But the important thing is that 2 is less than infinity. Right, so we have that actually S is convergent, which means that S is absolutely convergent, which means that S is convergent. All right, so this is a convergent series. You didn't need the alternating series test for this. All right, so just because you see an alternating series, don't use the alternating series test immediately. All right, there are other things you have to do. The alternating series test is the last resort. Unless, of course, we say something like, use the alternating series test on the following series, which we may say. Okay, we're going to try one that's a little bit more difficult because we're going to have to borrow from other parts of the class. All right, we're going to have to sort of utilize all of our knowledge. Okay, so let's start from the beginning on an example, and we'll do absolutely everything. So here's our example. It's the sum of n equals 1 to infinity. It's going to alternate, and here is the summand. And I want to know, is this sum, which we'll call S, is S convergent, divergent? And in the case that it's convergent, is it absolutely convergent? Or is it conditionally convergent? Okay, so let's walk through all the steps. We have no idea what this sum does. So what's the first thing that we should do?
Check this divergent.
Yeah, let's just check to see. So this thing will definitely diverge if these terms don't converge to 0. So is it the case that the limit of n goes to infinity of minus 1 n plus 1 over n squared over n cubed plus 1? What is this limit? Just forget about this because we could use squeeze theorem if we really wanted to. What's the limit of the remainder? Oh, we're all getting really tired, but this worries me. How would you do this? This is one of the most basic limit keys that we can do.
N squared over n cubed because they have the highest.
Well, what did we learn at the beginning of the year, right? We're just searching for the highest term. Okay, so if I were to divide everything here, I'll do it, but we shouldn't have to. If I take this to infinity, I'll forget about that. Well, I have that alternating. No, I might as well write it. This is going to be 1 over n cubed. N squared over n cubed over 1 plus 1 over n cubed. Okay, so what happens to this? Well, this really is 1 over n. So if I push n to infinity, what do you get? What does this turn into? What does this turn into? So what are you left with? 0 over 1, 0. Okay? That concerns me. That should have been immediate. I don't mean to make you feel bad. I wish to light a fire under your feet. Right? 8 days. Okay. So the limit of the terms here goes to 0. So what can we conclude?
Converges to 0.
That the series converges to 0?
No, because there's a negative.
What can we conclude here?
But it's not divergent.
No.
Oh, got it. Wrong.
That's the closest one, though. Nothing. You can basically conclude nothing, right? Because we can conclude S may be convergent. That's what we can conclude, right? So if we checked, because it may have diverged trivially, and then we could have stopped, right? So, okay, so we've determined that S maybe converges, which is sort of useless. So let's move on to the second test, right? So this is the first thing that we did. I don't really know what the name of it is. Divergence testing? I don't know. So the next thing we should check is what? Absolute convergence, right? That's the next easiest thing to do. So what is the, can we check the absolute convergence of this? So we have to think about this. Okay. How do you work with this? We did it earlier on in the class. Okay, we'll rattle off the tools that we have.
How do we do the limits, the ratio limits or something like that?
I don't think a ratio test would be that easy to deploy here. Limit comparison test. Okay, the limit comparison test is the one that you have to use. So notice what's true about so this is how I sort of look at this. Eventually in the limit, if you push n really big, what does this look like? That 1 doesn't make a difference if it's really big. So really you're left with 1 over n. So eventually you're just summing up 1 over n. And what do we know about 1 over n? Okay, it's divergent. So I think I should compare this with the divergence harmonic series. So let's take this and compare with this using the limit comparison test, which means I just have to study the ratio of their limits, the ratio of their terms in the limit. So that's going to be the limit of n goes to infinity of this n squared over n cubed plus 1 divided by that, which is just an n, which equals what? What's the limit of this? N, who said 1? A plus for you, sir. Right? This is 1. Right? Because you just have to, like, it's n cubed over n cubed. You ignore all but the highest terms and just look at their coefficients. So we get 1 here. So what does the limit comparison test tell us? I was going to keep repeating it until it sticks. Yeah.
Because that is divergent, the whole thing is divergent.
Yeah. Okay, so since this is a finite limit, the limit comparison test tells us that this series and this series will converge or diverge together. This is a divergent series. Therefore, this is divergent. So, S is not absolutely convergent. So we still don't know anything about this series. Okay, so at this point, our only recourse is to use the alternating series test. But I've conducted every other test beforehand, hoping that one of those easier ones would work. Right? Because now this series test that we're going to use, the alternating series test, like the second condition is actually not always easy to deduce. Okay, so S is not absolutely convergent. So the only type of convergence possible here is conditional convergence, if it conditionally converges. So let's check for 3. I should have used, well, I'll have to use 1, 2, 3 again. Are we conditionally convergent? Let's try to check this now. Okay, so on this board, let's start. So we have to first ask for what? What is our u in this case? And I'm going to ask you, miss, what's our u? Yes, that's correct. So un is going to be n squared over n cubed plus 1. All you have to do is essentially take the absolute value of that. Just drop all the negatives. Okay. Numerator is what? Positive? Denominator is what? Positive? All right. I'm comfortable now saying, look, as long as n is greater than or equal to 1, we have that un is greater than or equal to 0. Right? I'll give you full marks for that on a test. That's obvious enough. Okay, so we have checked, I'll say limit comparison test 1 has been checked off. What's the next thing that we have to deduce?
K plus 1 is smaller than.
Yes, we have to now ask if un plus 1 is less than un. Okay? This will be the hardest part of this question, surprisingly. So give that a try, but don't do it the way that I showed you. Well, or try to do it the way that I showed you and convince yourself that that's going to be hard. And then think what else you can do instead. Okay? So I want you to try and demonstrate that this is decreasing. That's a strong hint. Can I erase this part of the board? Yep. Does anyone know of the video game Oxygen Not Included? It's currently ruining my life. Look it up and play it. Yeah, I'm just saying, don't get too wrapped up in this. I just want you to prove to yourself that it's not going to be easy.
Just what? Just reduce the form, so it's 1 over n, and then compare it to 1 over n plus 1.
Un? So you want to just say that's 1 over n and compare it with 1 over n plus 1?
Wow.
Like if our sum is going to infinity, like in this case.
Yeah, I'm just trying to think. Like that observation's not incorrect. I I'm trying to think of like how we would take that and then like make it an argument. Because you have to say like okay, so this UN, far enough, if we go far enough down the series, will eventually just look like 1 over n, which is less than 1 over n plus 1. No, but yeah, but then you're comparing like UN and UN plus 1 like at infinity, which are essentially like the same. Like, you see what I'm trying to say? You're making a comparison at infinity, and that's not strong enough. Because this has to be true everywhere. Right? Like, at a point, it has to start being true everywhere. So you should be able to really deduce. Right? If you said n had to be bigger than 10 million, you should then still be able to produce an argument that says, okay, once n is 10 million, then here's my argument for this. But like that's not a bad intuition, right? For when you're saying, oh no, this should be decreasing, right? Because we don't even know. I sort of just told you that it's decreasing, but we don't really know that. How else could we establish if something was decreasing?
Can we find the derivative?
Yes.
Compare which one has negative slope or the more negative slope?
The more negative slope.
Because that will tell me this one is decreasing faster. Which one is
The first thing you said, sensible. The second thing you said is
Which one has a greater magnitude of
which one of what? Of what?
Which of the two derivatives? I was going to do n plus 1 and the regular.
You don't need 2 derivatives. You don't need 2 functions. You need 1 function.
Oh, and then you just sub in this one into the derivative of that.
Okay. Consider the function x squared over x cubed plus 1. What's true about that function? It's un at every integer point. Yeah. So if that function is decreasing, then un is decreasing. Follow that?
You should ask me questions, I don't know this.
Okay, so that n squared over n cubed plus 1, right? They're like individual points. Right, just swap out n with an x, so all x zero values. Then you actually have a curve. My curve hits all the points on that. But we know that curve using calculus is decreasing. Like if you take the derivatives and show that it's everywhere negative. Okay, if something has everywhere negative derivative, it's going down. If that function's going down and it's passing through all the points of un has to be going down. Here's an example where we have to borrow some old technology. Okay, you guys give up yet? Have you proved to yourself that this is kind of difficult? Okay, so I'll show you the trick. This is a good trick. What is true about this function? Okay, so we want to show, recall I want to show essentially that un is decreasing. So consider this, or notice, if I have the function, real valued function, such that x goes to what is x squared over x cubed plus 1. I'm just using the flourished, I don't know, you're more used to this. I just wanted to emphasize that this is a real valued function. So what's true about this f of x? Well, notice that f of 1, or rather, what do we have to start? Is it 2? I erased the question. What was the original question? Anyone? What was the index starting at?
N equals 1.
All right, and it was the alternating n cubed plus 1. Okay, so from 1, so what's f of 1?
This multiplies by n squared over n cubed.
Oh, I'm missing an n squared. Okay, what's f of 1? Yeah, but like, what I want for you to notice is f of 1 is equal to u1.
Yeah.
Huh? That f of 2 is equal to u2. That f of 3 is equal to u3, and so on. Does everyone follow this? It's crucial. Tell me if you don't. All right, I just defined a function which happens to go through all of the terms at integer points. Okay. What would we be able to conclude if f was a decreasing function? If I could do this, that would bring those down here. And then what could we conclude about what can we conclude about these u's, right? Was it the other way?
Yeah.
Oh yeah, you're right. Thank you. Yes, decreasing. Thank you. Okay. So if f is decreasing, this means that un is decreasing. So can you prove that f is decreasing?
Yes.
Yes, using goddamn derivatives. Someone tell me how we can prove that f is a decreasing function.
First derivative. And then you just compare it. By doing the integral test?
Whoa. F is decreasing over this interval when f prime of x is negative for x in the interval. Don't forget about all this optimization that you learned, right? Right, this means you have downward slope. Right? The function has to be going down. So all I have to prove is that at least in our range, at least for x greater than 1, that f is decreasing. So can we prove that? I think you guys are all just tired. I understand that. Okay, so what is f prime of x? Can we at least remember how to take derivatives? Use quotient rule. Okay, using quotient rule, you eventually find that this is x, 2 minus x cubed over x cubed plus 1 squared. All right. When is this positive and when is it negative? Let's do our old sort of critical point investigation. So what do you notice about the numerator here? Always positive, so that's not going to contribute to this sign. We also know that x has to be bigger than 1. That's where we're starting. So if x is bigger than 1, what does that mean about this? Positive. So what's the thing controlling the signage of this function? Well, 2 minus the x cubed. Oh yeah, cubed root of 3. So the only thing that can change the sign of this fraction is this term. So when 2 minus x cubed is less than 0, or equal to, less than 0, then we know that this function is decreasing under these conditions. So these conditions actually say this is when x is bigger than the cubed root of 2. Cubed root of 2 is not 2. So I can just say basically, as long as x is greater than 1, we are decreasing. Okay, so this is enough, right? So I have established that I can put these in, right? So thus, f is decreasing for x bigger than 1. Thus, un is decreasing, which gives us limit comparison test part 2. And what's the final thing that we have to check? Yeah, what's the limit of our u as we go to infinity? Yeah, we already said it was equal to 0. That's a check we already made. So we actually already have that the limit as n goes to infinity of un equals to 0. That's the limit comparison test part 3. So from this we can conclude that the original sum is conditionally convergent, which is the weakest type of convergent. Right, but we used all the tools to get there. We were hoping that it was divergent. That was the easiest thing to check. It wasn't. The next thing we were hoping is that we would get absolute convergence. It wasn't. Well, then the last thing on our plate, or the last thing in our toolbox, is to use this limit comparison test, and we found it. Had it failed, we'd still have no information.
So
It'd be inconclusive. Right? Failing the limit comparison test doesn't tell you that the thing diverges. Right? It is a one-way thing. If these are true, then this is convergent. It doesn't say when these things aren't satisfying that it is not convergent. So you can do a lot of work and get no information still. Then you'd really have to try to do some experiments, like go to a computer and see if this thing is indeed increasing. Okay, but like essentially it's the same 3 steps each time. And like this one you should be doing anyways. So it's really 2 steps. You guys want to try one? Let me see. Because it seems that you guys are really exhausted. Okay, so maybe we'll try one more, and I'll give you a little bit of working time. So where can I write this? So I want you to tell me about the nature of convergence for this sum. Four over 7 minus 4 over 8 plus 4 over 9 minus 4 over 10 plus 4 over 11. Okay. Is this, tell me about the convergence. Is this convergent or divergent? And if it's convergent, is it absolutely convergent or is it conditionally convergent? Give that a go.
Can we do a very similar example, like the very first one, but it was 1 over the value instead of 4?
Yeah, give it a try. I'll write some other ones, I think. And these aren't necessarily alternating series tests, right? I'm just giving you random ones. Just work on these. Let's call it for the class. You guys are been working really hard, so get some rest. But 8 days, 1 more class. We'll have class on Tuesday, but it's an open work period. So I'll come here.